Earth and civilization as we know it has come a long way in the past 200,000 years and has experienced a multitude of changes in that time. The human species has only existed for a mere 0.0015% of the immense 13.7 billion year age of the universe. However, humanity has conquered some of the most daunting tasks in that time period. We have come from hunting and gathering in the fields of Africa to colonizing the entire planet in a time period that is relatively a blink of an eye on the cosmic level. Some of the greatest minds that ever exist have helped push modern civilization forward and achieve goals that were once thought to be impossible. In just the past 150 years, we have gone from being stuck to the Earth's soil to landing on our closest cosmic neighbor, the Moon. Humanity's success is nothing short of spectacular, but on the universal scale, we may be rather insignificant. What would happen if we met an advanced alien species with technology more advanced than we could ever imagine?
A Type 3 civilization sounds amazing, but it's quite sad that none of us here right now could ever be alive to watch humans become a Type 3 civilization. But there is a way that you can experience what a Type 3 civilization could look and feel like right now, from the comfort of your own home. If you're interested, I highly recommend you check out the game Star Trek Fleet Command. Star Trek Fleet Command is a 4X MMO game set in the ever-expanding Star Trek universe. You can recruit legendary characters to crew iconic ships from over 50 years of Star Trek stories, and send them on missions of exploration to expand your territory. I actually really enjoyed the open world feel of this game, traveling across the incredible vast space landscape from Alpha to Omega Quadrant, and just seeing the beauty of our universe through the game's stunning graphics was truly mesmerizing. With a huge player base and a thriving community, you can make alliances and battle with people from all over the world. The game's latest update introduced Wave Defense, where groups of players defend a central point from waves of increasingly powerful enemies. This is an amazing way to socially interact in a way that transcends alliances. This new update also added the storyline of Aftermath of the temporal Cold War plotline from Season 3 of Star Trek Enterprise. With new extras like 10x core Star Trek Enterprise themed missions and 10x side missions, as well as new Enterprise officers, including Trip Tucker and T-Paul. They've also added an immersive story set in the Kelvin timeline, and are offering every new player 10 epic shards of Captain James Kirk for free using the promo code WARPSPEED, only available for new players. To get started completely free traveling across the Star Trek universe, click the link in the description down below, or scan this QR code to install the game on desktop or mobile, and become a leader of a Might Alliance today.
In 1964, a Soviet astronomer by the name of Nikolai Kardashev introduced a hypothetical scale that could be used to measure a potential civilization's level of technological advancement based on the amount of energy the civilization can produce. It is known today as the Kardashev scale. The scale has three traditional types, but many extensions and modifications to the scale have been proposed since its creation. The scale is logarithmic, meaning, as we go on, the amounts of power the civilization has gets much more substantial. In 1964, Kardashev defined the three base levels of civilization based on the power available to them. Type 1, the smallest of the original types, is also called a planetary civilization. This is most similar to our good old friend, Earth. Type 1 civilizations are capable of storing and using all of the energy which reaches this planet from its host star, which, in our case, is the Sun. This amount of energy would amount to an enormous 7 times 10 to the 17 watts. Notice how I said most similar though, as our modern civilization here on Earth does not quite exactly fit into the Type 1 civilization category. Yes, I know, we pathetic humans can't even fit into the lowest level of the advanced civilizations. Rather than fitting into a Type 1 civilization, we humans lie in one of the extended types of civilizations, Type 0. You see, when this scale was proposed, famous astronomer and astrophysicist Carl Sagan produced a formula to define a certain hypothetical civilization's Kardashev rating. This is that formula, where K represents a hypothetical civilization's Kardashev rating, while P represents the amount of power the civilization uses in watts. A proposed Type 0 civilization will control approximately 1 megawatt, or 1 million watts of power, which is minuscule compared to the amount of power we use on a daily basis. In 2015 alone, the total world energy consumption was 17.35 terawatts, or this huge number. Plugging this number into P and cranking out the numbers, our Kardashev rating as a civilization would be approximately a Type 0.72. Even as a civilization with 7 billion humans on our planet, 12 of which ventured to the moon, with spacecraft sent billions of miles into the abyss of interstellar space and plans to colonize Mars in the near future. We still only score a measly 0.72 on the Kardashev scale. According to Carl Sagan, humanity is going through a phase of technical adolescence, typical of a civilization about to integrate the Type 1 Kardashev scale. Michio Kaku, another brilliant theoretical physicist, suggests that humans may attain Type 1 status in the next 100 to 200 years, Type 2 status in perhaps the next few thousand years, and Type 3 status in 100,000 to 1 million years. This really goes to show the truly immense timescales it would take to advance to the next type of civilization. However, we are heading towards becoming a Type 1 civilization in the next couple hundred years or so, and this is a huge step for humanity. As a Type 1 civilization, we would have complete control over our own planet. Perhaps we could influence the weather, change the geological makeup of our own planet, and much, much more. However, even this amount of power is tiny compared to the next type of civilization, Type 2. A Type 2 civilization, also referred to as a stellar civilization, can control the total energy of its host star and transfer the energy throughout the entire solar system. One popular hypothesized device used to harness the entire energy output of a Type 2 civilization's host star are called Dyson structures. You may have seen these before, as they are rather popular in science fiction. The name was coined by Freeman Dyson, and is essentially a system of orbiting solar power satellites. Basically, it's an insanely massive hollow sphere built around a civilization's host star to milk all of the energy from it. Zephyrus made a great video on this idea, and you should definitely check it out. I'll be sure to leave a link to it in the description. But back on topic. Another rather exotic idea to harness energy for a Type 2 civilization would be to feed a stellar mass, for example, a star, into a nearby black hole and collect the photons emitted by the accretion disk. Now, how a civilization could somehow deposit a star into a black hole is beyond me, but it is a means of energy nonetheless. A Type 2 civilization would not only build these supermassive structures, but would control and live within them. They would control every single planet in their solar system, mine all the asteroids at their leisure, and essentially do whatever they want inside their solar neighborhood. The amount of power the civilization would have is remarkable, but is nothing when compared to a Type 3 civilization. A Type 3 civilization, also referred to as a galactic civilization, can control the total energy of its entire host galaxy. The amount of power this civilization would have is truly frightening, and is sorta in the realm of science fiction, but I'll cover it anyway. You see, this civilization would function extremely similar to the way a Type 2 civilization would work. It would harness the power of stars, mine planets and asteroids, and so on, but not only for one star, but for billions of stars. A civilization such as this would use planets and solar systems like Legos, building and deconstructing planets to build up their empire elsewhere in the galaxy. The galaxy would seemingly become their playground, and everything they do and use is merely a toy. Harnessing the energy of quasars would be like hitting the lottery for them. The supermassive black hole at the center of their galaxy could be used as an energy source for a Type 3 civilization. Galactic real estate would become a reality, with planets, stars, or even complete solar systems being auctioned off by some supreme leader. Interestingly enough, this hypothetical galaxy may not even be noticeable. If such a civilization did exist, all of the energy from the stars would be held and used for whatever the civilization may need. This means all the starlight, gas, and elements in an entire galaxy would become like your kitchen pantry. If all of the matter in their entire galaxy was exploited for energy, an outside observer would view the galaxy to be completely invisible. It would appear as if there were a hole in the galaxy, or, if they have colonized the entire galaxy, perhaps nothing at all. There is a place in space known as the Great Void. At nearly 330 million light-years in diameter, the Great Void is one of the largest known voids in the entire universe, and is commonly referred to as a supervoid. This region of space is seemingly devoid of life and galaxies as we know it. A region of space with such a massive size as the Great Void contains, scientists estimate that there should be at least 2,000 galaxies in this area of space. But, to date, there have only been 60 galaxies that have been discovered in the Great Void. This is a mere 3% of the amount of galaxies that should occupy an area this large. So, where are they? Could it be Type 3 civilizations completely dominating an entire region of space, milking a 330 million light-year wide region for resources? Leave your thoughts in the comments below, and I'll be sure to respond to them as quickly as I can. Thanks for watching.
The universe is a mind-boggling place. Actually, I'm not even sure I can call it a place. NASA says the universe is everything, but what they really mean is that it contains everything. All of space, energy, time, and matter like you and me. But there's more to it than meets the eye. Literally. All ordinary matter, like the particles that form us and everything else we can see, only comprise about 5% of the universe. So far, that's all the stuff that makes up our stars, planets, and galaxies, and we've only been able to see about half of all of that with our telescopes. The rest is entirely invisible. It's as if the universe doesn't like being put under our microscope, or telescope, to be more precise. Around 27% of our universe is dark matter, which emits no light or energy, and can't be detected by conventional sensors and detectors. We don't even know what it's really made of, and to be completely honest, we're not even sure it exists. We can only assume. To be fair, we have strong reason to believe dark matter exists. As early as the 1920s, astronomers hypothesized that the universe must contain more matter than we can see because the universe's gravitational forces appear stronger than the visible matter can account for. It's a simple matter of math. Okay, probably not simple math, but you get the idea. As if this wasn't confusing enough, the remaining 68% of the universe is made up of dark energy. Just like dark matter, dark energy is purely theoretical. It popped on our radars in 1998 when the Hubble telescope discovered that, in the past, the universe expanded at a slower rate than it does today. And if the universe is now growing at an accelerating rate, then there must be a force countering gravity and causing this acceleration. Wait, did I just describe repulsive gravity? As you could see, or can't actually, there's a lot of speculation when it comes to developing a blueprint for understanding the universe and everything in it. Even if we focus solely on the visible 5%, there's still a lot to unpack. The universe is a very confusing place, but subjects like math and physics make it easy for us to understand and appreciate the beauty in its chaos. Next time you find yourself gazing at a sky full of stars, take a moment and try to count how many you can see. Let me help you, on a clear night there's about 6,000. But if we wanted to calculate the number of stars in the entire universe, first we'd have to count the galaxies, and to do that, astronomers take very detailed pictures of small parts of the sky and count the galaxies in those pictures. They then multiply that number by the images needed to photograph the entire sky. Are you ready for the answer? There's approximately 2 trillion galaxies in the universe. 2 trillion clusters of dust swirling in a mostly invisible universe, harboring countless stars, planets, and even civilizations. Our Milky Way galaxy alone is home to 100 billion stars. Using this number as a standard, we can predict that there are roughly 200 billion trillion stars in the universe. A staggering number, I know. It's about 10 times the number of cups of water in Earth's oceans. In our galaxy, the Milky Way, every star has at least one planet orbiting it, meaning there are at least 100 billion exoplanets in our galaxy alone. To date, NASA has discovered more than 5,000 of them. The big question that has been haunting us ever since we developed the mental capacity to ponder our existence in this vast universe is still unanswered. Are we alone in the universe? Well, according to Enrico Fermi, a Nobel Prize-winning physicist, considering the young age of our solar system compared to the much older age of the universe, in that interstellar travel should be easy to achieve given enough time, Earth should have been visited by intelligent aliens by now if they did exist. This interpretation became known as the Fermi paradox, and it provides no consolation to our lonely existence. But what if life isn't as unique as we think it is? What if the universe is teeming with countless species far more intelligent than we are? Species that know of our existence and even visit us, only to deem us unfit or too primitive for interaction. Think about an ant colony that you happen to come across through your walk in the park. Would you try to communicate with them? It would be pointless, wouldn't it? If you're having a bad day, you might even go out of your way to step on them. Maybe our entire existence is equivalent to an ant colony placed in this region of the universe by some sort of higher intelligence, an isolated experiment with no particular purpose. Alright, I'll admit that's a bit dark. Let's bring some light back into the equation. Light is the fastest thing in the universe, and in a vacuum it can travel at speeds close to 300,000 kilometers per second. To put that in perspective, light can circulate the Earth 7.5 times in just 1 second. Even at these insane speeds, it would take light 92 billion years to travel across the observable universe. Yes, that's where the measurement light year comes from. Light is strange. It's an electromagnetic wave of massless particles called photons that travel outwards in straight lines. But how can it travel around the Earth if it moves in straight lines? Maybe Earth is flat, after all. I won't get into that right now, but I made an entire video about it. You should check it out. Spoiler though, it isn't. While light does travel in straight lines, it can also be bent by gravity. Contrary to what we were taught in school, gravity isn't a force. It doesn't pull anything downward. Instead, it just curves the fabric of the universe. If you're confused, don't feel bad. Gravity has confounded the best of us. Winston Churchill famously said that gravity is a riddle wrapped in a mystery inside an enigma. But we've put our best scientists on it, and while Newton gave us a good understanding of gravity, it was Einstein who cracked the code. To do so, Einstein first had to reimagine three-dimensional space by adding time to the equation. The outcome is a four-dimensional construct called Spacetime, and a mass like the Sun warps this fabric by creating a valley, and then planets like Earth circle around the valley like a ball around a roulette wheel. This is what we call the force of gravity. Einstein had quite the imagination. Before he was recognized as a genius, he worked as a patent clerk and had a lot of time to think about, well, time. In his special relativity theory, Einstein proved that time is relative to the observer, meaning that when an object is moving really fast, it experiences time more slowly. For example, in 2015, astronaut Scott Kelly spent nearly a year on board the International Space Station, which meant that he was moving much faster than his twin brother Mark, who was on the Earth's surface. Based on Einstein's special relativity theory, Mark aged 5 milliseconds more than his brother did in space during this time. This is called time dilation, and while 5 milliseconds doesn't seem like much, at speeds approaching that of light, time dilation can have much more dramatic effects. If a 15-year-old leaves Earth traveling at 99.5% the speed of light for 5 years, upon returning to Earth, they will find that they've aged only 5 years, while everyone else has aged 50. Mind-blowing, I know, but time dilation isn't exclusive to speed. Gravity can also slow time. The bigger the mass of an object, the bigger the warping of space-time and the slower time moves. It's believed that time freezes entirely at the edge of black holes, at the event horizon. Who knows, maybe time even moves backwards inside black holes. Speaking of black holes, in the 1990s, the Hubble telescope discovered that black holes aren't as rare as we thought they were. Almost every galaxy we know of, including our Milky Way, has a supermassive black hole at its center. We still don't know what they're doing there, but they must have played a significant part since they're at the heart of every galaxy. Maybe galaxies gave birth to black holes, or black holes to galaxies. You know, your typical chicken and egg situation, but on a cosmic scale. Observations from the Hubble tell us that galaxies were born around 1 billion years after the Big Bang, and we know that the Big Bang was created out of a singularity, an infinitely small, hot, and dense point, which is the exact definition of black holes. Could our universe have been born out of a black hole? It very well could have. Have you ever wondered what was there before the Big Bang? Was there a time before time itself? As creatures of time, it's hard imagining a time without time. Okay, this time I'm done talking about time. I'll leave this topic for another video. Here's one to make you gasp for breath. Every atom of oxygen in your lungs, carbon in your muscles, calcium in your bones, and iron in your blood was created inside a star before Earth was born. Apart from hydrogen, every other ingredient in our body is made from elements forged by stars. Stars are basically giant element furnaces. Their intense heat can cause atoms to collide, creating new elements like iron and carbon. Now, aren't you glad there are 200 billion trillion stars in the universe? If you're feeling overwhelmed by the true immensity of it all, you can take a step back and focus your energy inward. There are around 7 octillion atoms in a 70 kilogram or 150 pound body. That's 7 billion billion billion, and these atoms are made up of even smaller fundamental particles like electrons. The study of matter and energy at the smallest fundamental level is called quantum physics, and believe it or not, we still don't know much about it. An electron, for example, can exist in 2 places at one time. It's called superposition. If we're made of electrons and other quantum particles, why can't we be in 2 places at once? Is there something I'm missing here? As I said, quantum physics is a mind-boggling field, but unlike dark matter and dark energy, at least we can observe quantum particles, right? Well, we can, but it's a bit more complicated than you might think. One of the most bizarre premises of quantum theory is that the sheer act of observation can alter the observed reality. One of the most famous experiments in physics, the double-slit experiment, demonstrated that particles like an electron could have wave-like properties, and suggested that simply observing the electron can dramatically affect its behavior. Like most of the universe, it seems that electrons don't like being observed. They've been proven to be rather intimate with each other. Maybe that's why. Once interacting, subatomic particles can form unbreakable bonds even if they're billions of light years apart. It's called quantum entanglement and is still one of the many mysteries of quantum physics. Einstein called it spooky action at a distance, which sounds like an incredible name for a band. I'll admit, maybe diving into the world of subatomic wasn't such a good idea, but it was necessary. Finding a link between the very small and the large will be the key to understanding everything the universe offers. And despite everything we know, we haven't even begun to scratch the surface. At the end of the day, our existence in this cold and silent universe is as confusing as it is mesmerizing. But there's a certain kind of wisdom in not knowing. Maybe if we did, we'd have no reason to push the boundaries of our knowledge anymore, or worse, we'd have no reason to look up at the stars and just wonder. On a clear night, your patch of sky can be lit by as many as 6,000 stars, so whenever you can, look above and enjoy the cosmic view. You never know what you might discover. Have you ever looked up at the night sky and pondered about your very own existence? Maybe you were camping out with some friends, or all alone marveling at the big canvas of darkness plastered with countless glowing stars. Well, you're not alone. Looking above and contemplating the sheer immensity of the universe is something humans have been doing since the dawn of time. It's quite magical that recognizing you're part of something inexplicably huge and impersonal can elicit feelings that are so deep, reflective, and personal. Whenever you find yourself lost in these pensive moments, know that the universe, this ancient organism that we were somehow born into, is calling you on a spiritual journey that is in one way or another meant to guide you through your deep and existential emotions and help you find your place in its cold yet comforting grasp. The ancient Stoics understood precisely how immense our human problems could feel. They knew how a bad day at work could develop into a week of aggravation. They knew how a string of bad luck could become a gateway to depression. But they also knew how insignificant our problems really are in the grand scheme of things, and that once we fully understood this cosmic scale, we would truly become free. So if you're having a bad day or you just feel a bit out of sorts, find a quiet place and prepare yourself to witness the view from above for the first time. You're about to embark on a journey outside of your own body, a celestial adventure meant to help you understand the sheer size of our ever-expanding universe, and in the process, your place in it. Because only when you look above will you be able to understand what's within. So take a deep breath and close your eyes. Your journey across the universe is about to begin. Wherever you are right now, imagine yourself slowly lifting out of your body and floating in the vicinity of the room you're in. Observe your surroundings. You're no longer confined to the borders of your own body. Can you see yourself sitting there with your eyes closed, taking deep breaths? Looks weird, right? If you think about it, no one really knows you like you know yourself. People's perceptions of you are based on their own interactions with you. They have their own biases and judgments, and while some of them come close to knowing who you really are, none of them ever fully do. Floating around in your room, you can finally experience your true self. You can observe your body without being inside of it. The room you're in all its familiarity, could very well feel alien to you right now. You may have grown up in this room, spent years developing your sense of self, and yet, as you float around, none of it feels it's genuinely yours. As the abstract feeling of detachment swirls through your mind, you suddenly zoom out to observe the countless houses in your neighborhood or the endless apartments stacked in towering skyscrapers. People just like you wake up every morning and carry on living in the same houses, growing up in the same streets and leading similar lives. It's funny how we could be so physically close to each other and yet know nothing of one another. How many people live in your town or city? How many of them do you really know? What are their dreams and ambitions, their fears and insecurities? Do you think they're that different to yours? We tend to think that our human experience is so unique that no one, not a single person out of the nearly 8 billion of us on this planet, can begin to understand what we're going through. But the truth is, we're a lot more similar than we believe, and that should give us solace in the face of adversity. Look at the houses in your neighborhood, or the buildings stacked elegantly next to each other. They are all the same. As you witness this view from above, your heart will begin to fill with an unexpected warmth as you feel connected to every one of the humans inside those houses. It's like a piece of you lives in every single one of them. A lot of the towns in the US have populations of 1,000, and yet we still call them small. But aren't 1,000 people a lot? Try and imagine that number on a football field or a basketball court. Are these towns still considered small in your eyes? The United States is actually considered a nation of small towns. Out of a population of around 330 million people, data from the past decade shows that 3/4 live in cities and towns with fewer than 5,000 people. So I ask again, is 1,000 small? Continue to zoom out and you see the towns and cities that make up states bound by imaginary borders. Or are they really imaginary? There's around 40 million people living in California, basking in the golden sun of the Pacific Ocean. On the other hand, there are only about 732,000 people living an entirely different life in the cold of Alaska. The life of a Californian is very different from that of an Alaskan, even if both are just humans trying to make the most out of their puzzling existence. Our history has also drawn some real blood-stained boundaries, separating us and forcing us to focus on our differences rather than our similarities. Wars have claimed millions of lives, mostly in the names of ideologies of separation and alienation. As you slowly travel the globe from the American continent, you see how life can develop completely differently despite proximity. Throughout history, many countries fought internal civil battles and subsequently declared their own independence. South Sudan declared independence from Sudan in 2011, Kosovo declared independence from Serbia in 2008, and Montenegro became its own state after separating from Serbia in 2006. Many more have separated and declared their independence, which makes you wonder how defined we are by the countries we're born into. Are you still breathing? Your journey through planet Earth is almost over. You've lifted from your body, away from your hometown, out of your home country, and now you're floating in the atmosphere of our tiny blue planet, perhaps aboard the International Space Station. In 24 hours, this tiny space station orbits our planet 16 times. 16 sunrises and 16 sunsets. Imagine looking at the Earth as you orbit its 40,075 kilometers, or around 25,000 miles circumference. Except for the moon landing, everything that has ever happened in the history of humanity has happened on this planet. Everything we've ever experienced, every joy, every disappointment, every love, every broken heart. Our entire human existence is presently confined to this rotating globe floating in the vastness of space. And as it rotates at 16,075 kilometers per hour, time passes and washes away all that ever was and makes room for whatever there is to come. Our planet has existed for 4.5 billion years, but us modern humans have only been here for around 200,000 years, and civilization as we know it is only around 6,000 years old. You and me, if we're lucky enough, will only get to experience around 80 more of those years. Everything that has happened before and everything that will happen after, we can only imagine. The burden of our existence is nothing but a speck of dust in the cosmic hourglass. Looking at Earth from above could be daunting. Astronauts that live on the ISS almost always come back to Earth with a fundamental understanding of what it truly means to be alive, and what matters most in life. Take another long and deep breath. Let your lungs fill with the magnitude of what you've already experienced and what you're about to experience. You're going to journey further into space, deep into our solar system, and then into uncharted territory where no human has ever traversed. Leave all your human preconceptions behind and open your heart to the expanding universe. As you finally break free from the Earth's atmosphere, imagine yourself floating further to the edge of interstellar space, looking at our solar system as a whole. 8 planets circling around a glowing star. Each one of these planets has its own unique story, from Saturn's ringed beauty to the massive bulk of Jupiter and its great red spot big enough to engulf the entirety of Earth. But even Jupiter's incredible mass holds no candle to the centerpiece of our glorious solar system, the Sun, the star that holds our collection of planets together. Our Sun is 109 times wider than Earth and makes up 99.8% of our solar system's entire mass. Put everything you've experienced in the scale and then compare it to the sheer magnitude of our glowing star, and let it sink in for a second. Let's take a step further and slowly leave the safety of our solar system. Observe as the Sun itself becomes a small particle, barely visible from our astronomical vantage point. You look around you and notice the countless other stars, billions of glowing specks everywhere you turn. There are more stars in the universe than there are grains of sand on Earth, more than 10,000 stars for each grain, in fact. Most of these stars have planets orbiting around them, just like our solar system. If the primordial soup that spawned life on Earth managed to replicate on one of these countless planets, would it be similar to life as we know it on Earth? Would they wonder about their existence the same way we do? Would they understand how small and insignificant their problems are in the grand scheme of things? Imagine alien civilizations fighting through their own existence just like you and I. Imagine the struggle to exist in the universe every day. Planets that harbor life, that orbit stars, that make up galaxies that float around alone in space. You are now leaving the Milky Way and venturing further out into the still and silent darkness of the universe. Everywhere you look, there's a galaxy waiting to be explored. A galaxy that could harbor a star, that might have a planet that somehow managed to produce life against all odds. One more deep breath, and you're now looking at the entire observable universe. One big organism that is at least 92 billion light years wide. Now that you've been able to observe the universe as a whole, it's time to slowly bring it all back in. Let's find the Milky Way among the hundreds of billions of galaxies out there. Let's find our sun among the 100,000 million stars in our home galaxy. We're finally back in the solar system, passing from Neptune to Saturn to Mars, and finally Earth. You jump from the ISS and burst through the atmosphere and then cross the imaginary borders that are meant to separate us. Find your country, your state, your street, and then your home. Finally look at yourself breathing, taking all that experience in. Take one last deep breath and open your eyes. Next time you're feeling down or the world seems to be taking too much of a toll on you, contemplate your existence and remember this moment, this feeling, this experience. Let it remind you that whatever is weighing you down is only temporary. A minor setback in the grand cosmic scale. In the year 1609, Galileo pointed one of the first telescopes ever created up at the heavens, and what he observed sparked a revolution of curiosity that has been central to every single human generation since. Galileo saw mountains and craters on the surface of the moon, the arm of our Milky Way galaxy arching across the sky, and an endless universe riddled with countless stars. The mysteries of outer space were boundless, and the journey towards discovering them had only just begun. Over 400 years later, and our obsession with the enigma that is space has only managed to intensify, fueling many great technological advancements that have made our ever-expanding universe seem smaller and its boundaries closer than ever. On the 25th of December 2021, NASA launched humanity's most powerful telescope yet. More than 30 years in the making, $10 billion spent, a successful launch, 50 intricate outer space deployments, and a distance of over 1.5 million kilometers traveled from Earth, the James Webb Space Telescope has finally delivered its first full-size images of our universe, marking an era of space discovery that promises unique and unprecedented views from across our own solar system to the very heart of the universe. The James Webb Space Telescope, JWST for short, has been designed to look more than 13.5 billion years into the past to study the farthest and oldest regions of space, peering back into the early days of the universe. Its aim is to look at the first galaxies that started forming and emitting light right after the Big Bang. It's no wonder that scientists often refer to telescopes as time machines. In them lies the power to see what our universe once was, and perhaps answer one of humanity's most perplexing existential questions. How did we get here? And right now, Webb is our best chance at finding an answer to that question. However, to fully understand what makes Webb so special, we have to travel back in time to the year 1990, when the Hubble Space Telescope was launched. The Hubble Space Telescope embarked on a mission similar to Webb's. Its purpose, just like Webb's, was to study the universe like it's never been studied before, and to bring us closer to understanding our existence and our place among the stars. Over the past 30 years, Hubble has brought us images of galaxies we never knew existed, star clusters, and nebulae like we've never seen before. These images helped illustrate how in the early days of our universe, just millions of years after the Big Bang, cold clouds of gas and dust evolved into swirling, coalescing galaxies teeming with stars. Sadly, that was just how far Hubble could see. In order to observe how these first galaxies were born, we needed a bigger telescope, one that wasn't just more powerful, but that could also operate in the infrared. So just a few years after Hubble was launched into space, scientists began working on the next big telescope. Today, Webb is 100 times more powerful than Hubble, and its ability to observe infrared light opens up a new universe of possibilities. Literally.
Ever since Edwin Hubble discovered that the universe is expanding, we've known that galaxies have been receding at faster and faster speeds. Light from these galaxies is stretched to longer wavelengths as it travels through space, which is why they're only visible through infrared. Hubble, the telescope, is only able to see light on the visible spectrum, which means it's limited in the amount of information it can fetch us about these earliest galaxies. But with Webb, we finally have the ability to observe them. To detect these infrared waves, Webb traveled more than 1.5 million kilometers away from Earth's warm atmosphere, to a very cold region in space that is protected from our planet's infrared radiation. Built into this telescope are huge sun shields as big as a tennis court that protect it from the rays of the sun and help keep its temperature at minus 233 degrees Celsius, so it can be cool enough to detect infrared radiation from the early days of the universe. This is the first time in history of our species that we've been able to look at our universe with such depth and detail. And the first images NASA released on July 12th are proof that we've entered a new space frontier that is bound to bring us closer to understanding our place in this ever-expanding universe. Let's begin our journey back in time with the closest image Webb has taken. This is called the Southern Ring Nebula. It's a planetary nebula in our own Milky Way galaxy, 2,000 light-years away. Despite its name, a planetary nebula doesn't have any planets. The name is simply inspired by its round structure. A nebula is clouds of dust that are thrown out by the explosion of a dying star. You can see enormous clouds of gas thrown out by this red giant in the center of the image. This image utilizes Webb's near-infrared camera, or NIR cam, which looks at the shortest infrared wavelengths. When we switch to its MIRI, or mid-infrared instrument that can observe longer wavelengths, you can actually see that it gives us an unprecedented look into the heart of this nebula. Right here, you can actually see two stars at the center of the system, with the dimmer one being a white dwarf at the tail end of its life, and the brighter one, a red giant, at an earlier stage of its dying process. The pair of stars are locked in each other's orbit in a cosmic embrace, which leads the dimmer star to spray ejected material like a sprinkler, resulting in these jagged rings. Stars are critical to life as we know it. With Webb's powerful mirrors and its ability to peer behind the thickness of gas and dust, we'll be able to study the death of stars like we've never done before. This could give us a greater understanding of the chemicals and the elements that are discharged from stars as they evolve through time, and whether these components are the building blocks that are needed to spawn life as we know it back on Earth. But the birth of stars is just as important as their death. This image of the cosmic cliffs in the Canary Nebula, 7,500 light-years away, offers a breathtaking view of the clouds of gas and dust actively coming together to form new stars. This is one of the most active star-forming regions in our galaxy, a star nursery that could give us tremendous information on this creation process. When we switch to the MIRI once again, you can see the infant stars behind this ethereal cloud of dust. Being able to see what is behind their cosmic clouds is incredibly important when we look at galaxies as a whole. It can enable us to estimate the total mass of stars in a galaxy with more accuracy. Speaking of galaxies, 300 million light-years away lies the tightest galaxy grouping we've ever discovered. These 5 galaxies are called Stephan's Quintet, and they are all bound to crash into each other and eventually merge. Actually, 2 of them are already in the process of doing exactly that. This image of Stephan's Quintet is the largest of Webb's initial images. It might not look like it at first glance, but what you're seeing here is actually a composite of over 1,000 images made up of over 150 million pixels when combined together. Zooming in on any part of this picture will show you hundreds, if not thousands, of galaxies waiting to be discovered. What's even more fascinating is that when we switch to the mid-infrared instrument, we can spot never-before-seen details of Stephan's Quintet. That very bright structure in the uppermost galaxy is actually a supermassive black hole, 24 million times the size of the Sun, and actively increasing in density while emitting more energy than 40 billion suns put together. Just pause and think about that for a moment. These new images provide us with valuable insights into galactic interactions that may have driven galaxy evolution in the early universe. The early universe, Webb's primary mission. This is what is called a deep field image. Deep field is a long-lasting observation into a particular region of space, intended to collect light from the faintest, furthest objects. Peering 4.6 billion years into the past, this image shows the galaxy cluster SMACS 0723 at its center, alongside shimmering stars, warped light trails, and thousands of extremely distant jewel-like galaxies. It's the deepest and sharpest infrared image of the early universe we've had so far. But despite its magnificence, What's most interesting about this deep field is the warped light trails around the galaxy cluster's edges. This galaxy cluster is so massive that it warps spacetime, and ultimately the light of stars and galaxies located billions of light years behind it. This is called gravitational lensing, and acts like a cosmic magnifying glass, bringing the light of galaxies almost 13 light years away, potentially making them some of the oldest galaxies we've ever observed. Without a doubt, these early images are breathtaking and already showcase the huge capabilities of Webb. But taking pretty pictures isn't the telescope's only superpower. It can also study the atmosphere of planets. For a while now, we've been searching for exoplanets, which are planets outside our solar system, orbiting around a star similar to our Sun. We've discovered about 5,000 of them so far, with our main goal being able to find one that's hospitable to life, and ultimately finding some of that life. When analyzing the atmospheres of exoplanets, we look for elements such as methane, oxygen, or nitrogen, ingredients present in our own atmosphere that could signify the presence of life on these planets. So far, the universe hasn't offered us any signs of life. However, this graph captured by Webb of the hot gas giant exoplanet WASP-96b could be our first step towards locating some extraterrestrials. The observation reveals the presence of a very specific gas molecule, water vapor. While Hubble analyzed numerous exoplanets' atmosphere over the decades and detected water in 2013, Webb offers a more detailed observation, and a giant leap forward in tracking down habitable planets beyond Earth. This image is only a glimpse of Webb's massive ability to capture precise atmospheric elements hundreds of light years away. We've always wondered whether life exists beyond Earth, and Webb could be the tool to help us answer this question and change the meaning of our existence forever. The James Webb Space Telescope has only begun its journey, and the road ahead is still long and daunting. Analyzing the universe's origins, understanding the birth and death of stars, discovering distant galaxies, and finding exoplanets are only just the beginning. The truth is, looking more than 13 billion years into the past is bound to raise more questions than we could ever imagine, but it also has the potential to answer questions as well, some of which we've been asking since the days of Galileo, and even new ones we never knew we had. When Galileo raised his telescope to the sky and looked at the craters on the moon, he acted on an almost instinctual human curiosity that has been with us ever since the dawn of time. More than 400 years later, the same curiosity is bringing us even closer to our cosmic background. Earth is only a small stage in the cosmic arena, and with the beginning of a new era in space discovery, we now know that more than we ever did before. There is no doubt that in the upcoming years, Webb will bring the universe even closer to us and help us know more about the reality of our cosmic existence. So whenever you find yourself looking up at the night sky and its beautiful stars, remember, somewhere, something incredible is waiting to be known.
What if the term we typically use to define the confines of our very existence is just wrong? What is the true nature of the universe? Wait, am I even asking the right question? We're taught that the universe is all there ever was, all there is, and all there ever will be. I mean, that's the very definition of it, isn't it? But maybe we're not as confined as we think, and this idea isn't really a new one. The earliest recorded examples of the idea of infinite worlds can be found in the philosophy of ancient Greek atomism, which proposed that infinite parallel worlds were created from the collision of atoms. In the 3rd century, philosophers also proposed that the world eternally expired and regenerated, suggesting the existence of multiple universes across time. There's this prevailing idea throughout history of a group of multiple, parallel universes that comprise everything that exists, the entirety of space, time, matter, energy, information, and the physical laws and constants that describe them. And we're living in it. This is the multiverse. In 1954, this idea grew a bit more when Hugh Everett gave us the many worlds interpretation of the multiverse, the idea that quantum effects cause the universe to constantly split. He wrote it for his PhD thesis, but ended up having to publish a watered-down version when physicists at the time proposed the idea that every decision we make creates new universes to account for every single possible outcome. Presumably, each of those new universes also has the potential to do the same. It's enough to break my brain, or at the very least give me a pretty bad headache. But seriously, it's a cool thought. But is it just that? Does Everett's interpretation go beyond mere speculative reasoning? Is there any proof? Separating science from fiction when it comes to the existence of the multiverse can be really hard, especially when it's essentially all theoretical. It's important to remember here that the multiverse is not a theory in physics per se. Rather, it's an inevitable result of a series of existing theories in physics. And recent progress in cosmology, string theory, and quantum mechanics has brought about a revolution in thinking of sorts, with some even considering the multiverse as non-optional. You can't just opt out of the idea because you don't like it. It's there either way. You can apply this to a lot of things nowadays, actually. The existence of a multiverse is one thing that continues to divide physicists because, let's face it, we're looking for evidence of something that exists outside of our visible universe and leaves no trace within it. But wait, there are all sorts of things that we can observe that we know must be true. Decades before gravitational waves, disturbances, and the curvature of space-time were directly detected, it was largely accepted that they must exist because we had already observed their effects. The revolutionary periods of binary pulsars, spinning neutron stars orbiting one another, shortened. Something was carrying the energy away, and that thing was consistent with the predictions of gravitational waves. So that means there could also be indirect evidence for the existence of the multiverse too, right? Well, that really depends on which multiverse you think you're in. Yeah, there's a few options. So I'll circle back to the question of evidence. Let's take a look at some different types. One way of distinguishing between multiverse models is by looking at how connected universes proposed by each model are. That is, the extent to which they are part of a single system that is governed by the same physical and mathematical principles, and how much they potentially interact with each other. It sounds confusing, but just let me explain. Level 1 parallel universes are maybe the simplest and the most connected. It's suggested that space is so big, possibly infinite, that the rules of probability surely must allow for the fact that somewhere else out there are other planets exactly like ours. In fact, if our universe is infinite, as some suggest, then it would have infinitely many planets, and on some of them, the events that play out would be pretty much identical to those on our own Earth, with physical laws exactly the same as ours. It's like taking a deck of cards and shuffling them. There's a finite number of orderings that can occur, so if you shuffle the cards enough times, the orders will eventually repeat. In the same way, with an infinite universe and only a finite number of complexions of matter due to the laws of physics, the way that matter arranges itself surely has to repeat eventually. If only they weren't so far away from us. We're causally disconnected. This is why it's a parallel universe and not part of our own. We don't see these other universes, and you can blame the speed of light for that. Let me explain a bit more. Light started traveling at the moment of the Big Bang, around 14 billion years ago. And so it's impossible to see any further than about 14 billion light years. It's probably a bit further, since space is always expanding, but let's just try and forget that for now. This volume of space we're in is called the Hubble volume, and represents our observable and contactable universe. So we pretty much definitely can't travel or contact other universes if this scenario is true. But it's not entirely impossible. If you think level 1 parallel universes can happen, you're making two important assumptions. 1. The universe is infinite, and 2. With an infinite universe, every single possible configuration of particles in a Hubble volume would take place multiple times. Probably the most supported by sound theoretical physics are actually level 2 parallel universes. In these, it's assumed that regions of space are going through an inflation phase. Inflation is a hypothetical process of the early universe, and I know, more hypotheses, I'm sorry. It suggests that space-time would have expanded exponentially at a much faster rate than it is doing right now, faster than the speed of light. This would probably have been driven by an energy in the vacuum that would generate a repulsive force. This kind of exponential expansion would necessarily create a region of space-time unimaginably larger than our own universe. The result? A highly connected multiverse. It would probably be a relatively boring multiverse though compared to what I'm about to move on to, because similar to level 1 parallel universes, all of them would inhabit the same space-time, be subject to the same principles and physical laws, and would be composed of regions very similar to our own observable universe. Remember that deck of cards? Well, a level 2 multiverse would be like having multiple decks of cards that control different kinds of physical properties. What this does mean though, is that interactions between neighboring universes might, in principle, produce observable effects. A good way to try and imagine a level 2 parallel universe is to picture expanding bubbles in a shared background. If and when the bubbles collide, the result could be a bruise, appearing as a circular disturbance on the cosmic microwave background radiation. And here it is, finally, a hint of evidence. Well, maybe. The Eridanus supervoid, a cold spot in our universe, could hold some answers. Long story short, our knowledge of how the universe works would simply not allow for such a massive void. We know that as the universe expands, voids are created, but not enough time has passed since the Big Bang for such a large void to grow. Put simply, the odds of Eridanus existing are extremely unlikely, and it shouldn't be as cold as it is.
Scientists have also noticed that the distribution of heat in our observable universe is in fact asymmetrical, with higher than average temperatures recorded in the southern hemisphere, near the supposed void. It shouldn't be. In 2010, scientists analyzed some data. They thought that they found evidence to support the idea that the cold spot was in fact a bruise, where our universe collided with another. Disappointingly, there's not that much evidence. But that doesn't mean that the hypothesis should be discounted, especially since all other explanations for the existence of the cold spot are also equally unlikely. In terms of indirect evidence, there's actually plenty for level 2 parallel universes. First, cosmic inflation gave rise to the Big Bang, and gives us predictions for our universe that match what we observe. Second, we have quantum uncertainty, a rule governed by quantum mechanics. The values of certain pairs of properties in the quantum world can't ever be known at the same time with perfect accuracy. For example, both the speed of something and its position. You can measure one precisely, but you won't really know anything for sure about the other. Quantum uncertainty allows for a range in particle states and positions. This explains the fluctuations which gave rise to all matter in the early universe. But according to this rule, it's not just values of pairs of properties that can't be known accurately. There's also an inherent uncertainty in the value of a quantum field, a quantum measurement assigned to every single point in space. As time inevitably goes on, a field value that was certain at an earlier time now has a less certain value, so now you can only talk about it in terms of probabilities, not certainties. The value of any quantum field spreads out over time. A level 3 parallel universe is a consequence of the many worlds interpretation given to us by Everett. In these, every single quantum possibility inherent in the quantum wave function becomes a real possibility in some reality. It's based on an idea called superposition from quantum mechanics, which is to say that if an electron can exist in multiple places and multiple states at any one time, then why wouldn't we also exist in the same way, given that we're made up of these subatomic particles? When most science fiction fans think about the multiverse, they're most likely thinking about this model. The possibilities are quite literally endless. Level 3 parallel universes are different from level 1 and level 2 parallel universes in that they take place in the same space and time as our own universe. You still have no way to access them, even though you're continually in contact with them. In fact, every moment you live and every decision you make is causing a split of your current self into an infinite number of future selves, all of which are totally unaware of each other. Although, I guess now you are. And this gives rise to important ethical and moral questions, which I'll come back to a little later. The evidence for this type of multiverse is pretty indirect. The empirical evidence for quantum mechanics is simply overwhelming. Quantum mechanics simply demands the existence of the multiverse. It seems as if there's a pattern emerging. Level 3 parallel universes raise an interesting extra question that other models don't. Every decision you make may create any number of parallel universes where other yous and other people could either be negatively or positively affected by your choice. Your actions are not only shaping the course of just your life, but of countless lives of duplicates in other worlds. So, should we be considering our decisions even more carefully? Well, if you're aiming to reduce potential harm or suffering by doing this, of course you'd be more careful, whether we live in many worlds or just one. Shouldn't we aim to minimize suffering regardless? If there's even a small probability of a very bad outcome right now in this universe, wouldn't it be equally worth avoiding? A level 4 parallel universe perhaps has the potential to be the strangest place of all, and for this reason, it's also the most controversial prediction. We're talking about other universes here. Obviously, it won't make sense. Basically, any universe that you can get to work on paper would exist, based on the mathematical democracy principle, which simply means any universe that is mathematically possible has an equal possibility of actually existing. If the math works, chances are it could exist. That just covers the very tip of the iceberg of the different multiverse models and the science behind them. You can't really argue with all of that, right? Well, of course you can, and quite strongly. It's no secret that there's a strong opposition towards the idea of the multiverse itself and its general arguments. There's a quote, and it goes, "There's no reality without observation," which shuts down level 4 parallel universes right away. To be honest, these arguments are all valid. There's a ton of these potential weaknesses in the arguments for parallel universes, way more than I could ever cover here, and checking it all out in detail involves a lot of physics research and time that I really don't have or know how to do. I don't know whether the multiverse exists. I bet you're not really surprised about that answer though. But if modern physics is to be believed, our own universe shouldn't even be here at all. And if that's the case, then the same could be said for the multiverse. It really shouldn't be here either. But against all odds, just like ours, it just might be. In the year 1925, Einstein shared with a student his burning desire to understand the universe. "I want to know how God created this world," he said as they strolled along. "I'm not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are just details." This one conversation expresses the core of Einstein's guiding principle, one that has driven humanity to inquire, discover, experiment, and most importantly, learn about this universe we call home. But what was Einstein really talking about? And can human knowledge ever reach a point where we understand everything? Since the discovery of the world of quantum mechanics in the early 20th century, scientists have been racking their brain trying to understand how it works. Even a century later, we're still not sure how and why subatomic particles behave the way they do. But that's just half the problem. The discovery of quantum theory posed a more serious issue that Einstein, Stephen Hawking, and other world-renowned physicists have been working tirelessly to solve. That challenge can be summarized in one word: unification. You see, modern physics is split into two pillars: classical physics, the physics of Newton, Einstein, and Galileo, which predicts gravity and describes the motion of massive things in our cosmos like stars and planets, and quantum physics, which governs the world of subatomic particles according to its own set of laws and rules. Both pillars describe their respective worlds accurately, but fail when applied to each other's subject matter. Einstein's preoccupation was that there must be a way that these two worlds could reconcile. There has to be a theory that unifies the world of the subatomic with the world of the massive. A theory that can predict, well, everything. Now you might be thinking, so why should we care? Well, a unified theory that can bridge both of these worlds could potentially unlock many of our universe's secrets and answer some of the deepest philosophical and theological questions that we've been asking since the days of Galileo. What are we truly made of? What happened before the Big Bang? Are we living in a multiverse? The unified theory, or the theory of everything, might just have the answers to all of these questions. The universe and everything in it is glued together by four fundamental forces. I made an entire video on these four forces, so if you really want to fully understand all of them, I suggest you check it out. But for the sake of this video, here is the gist of what they do. Big objects like stars, planets, humans, and cats are all governed by the force of gravity. And thanks to Einstein and his general theory of relativity, we now know that gravity isn't a force that magically pulls objects together. Instead, it's the curving and warping of the fabric of our universe, spacetime. While all these big objects are governed by just one fundamental force, subatomic particles, on the other hand, are governed by three fundamental forces, as if they weren't already confusing enough. These three fundamental forces are electromagnetic, weak nuclear, and strong nuclear. Electromagnetism holds atoms together, the strong force holds nuclei together, and the weak force is responsible for some type of nuclear decay. These particles, along with their respective forces, make up what we call the Standard Model. The Standard Model describes the world of the very small. We know that everything in the universe is made of subatomic particles, from planets and stars to humans and dogs. We know that all of these things are made of atoms, and atoms are made of protons, neutrons, and electrons. In the 1960s, we discovered that even protons and neutrons are made of even smaller particles called quarks, and electrons from leptons. Using different combinations of these particles and their respective forces, we can build atoms, molecules, humans, planets, and even stars. So it seems that the Standard Model is a comprehensive interpretation of our universe. But it doesn't include everything. The truth is, finding the smallest subatomic particles is only the first step to getting to a theory of everything. The second step would be finding a place for gravity in this model. There are two reasons why gravity isn't included. The first is that when it comes to small particles, the force of gravity is so weak that it doesn't have any effect on a quantum system. The second reason is that we don't really know how to incorporate general relativity, which describes the motion of large objects, into the world of quantum that governs subatomic particles. Many great minds, including Einstein, tried tirelessly. It's said that even on his deathbed, Einstein revisited his notes on the theory of everything and tried one last time to find an elegant solution to explain the fundamental differences between the world of the small and that of the large. But unfortunately, he ran out of time. So that's that, right? While we still haven't found a theory that can explain everything, we have made significant progress, and maybe the most groundbreaking was that of another brilliant mind, Stephen Hawking. In 2014, a movie was made on the impactful life of Stephen Hawking. As a result, Hawking became one of the most revered physicists in the world, and one of the most admired by pop culture. Away from the limelight, however, Hawking, like Einstein, had an obsessive yearning to understand the universe and never ceased to challenge our knowledge of it. One of his greatest contributions was the discovery of what is now known as Hawking radiation. In 1974, Hawking discovered one of the biggest breakthroughs of the 20th century, a groundbreaking interpretation of black holes, as well as an unprecedented interaction between the world of quantum and gravity. Hawking's discovery was so ingenious that it gave us hope that the theory of everything, the holy grail of physics, is still a human possibility. Black holes are densely packed regions of space where the gravitational pull is so strong that nothing can escape, not even light. Einstein predicted the presence of black holes through his general theory of relativity in 1916, and we confirmed his predictions in 1974 when we observed our first black hole in the Milky Way. In the same year, Hawking discovered that black holes are like a vitamin tablet placed in water. They can dissipate in time and release energy. This is what we know as Hawking radiation today. But how can energy escape a black hole when nothing else can? Hawking used a quantum understanding to explain this. When we think of space, we imagine large, cold, empty places, but in reality, space is alive with the active creation and destruction of energy at the subatomic stage. Particles are created in pairs, matter and antimatter, and they are constantly created and destroyed in a concept known as annihilation. Hawking imagined a pair of particles created very close to the event horizon of a black hole. This is the boundary around a black hole from which nothing can escape. He then showed that these particles don't need to annihilate each other, since one of them can be sucked into the black hole. If the black hole is receiving negative energy, then it has to release energy in order for the law of conservation of energy to hold. Hawking also proved that black holes lose mass with time, and they don't last forever. But more importantly, he was able to arrive at this discovery by merging a quantum principle with the concept of gravity. This is by far the closest we've come to a theory of everything, a unified field theory, or quantum gravity. But as with most things in science, the fact that we haven't found that one elegant equation does not mean that we have failed. In fact, maybe the real treasure was the discoveries we made along the way, many of which have paved the way for a brighter future for humankind. String theory is one of the most prominent ones. It suggests that subatomic particles such as electrons and quarks are made of tiny vibrating strings or filaments that twist and fold, creating everything in our universe. Just like the strings of a violin, they can vibrate in various patterns, creating different kinds of particles, including the graviton, a hypothetical particle that, according to quantum mechanics, should carry the force of gravity. On paper, string theory could unite gravity and quantum mechanics under one framework once and for all. The theory was popularized in the 60s and 70s, and its mathematics predicts small bundled up extra dimensions that give rise to a network of universes, or a multiverse. While this theory is prominent, it's highly untestable, even with access to the latest technology. String theory, though, is only the beginning. After almost 2 decades of tireless research, we've discovered the Higgs boson. This proved that electrons and quarks inside the atom get their mass from an invisible field that spreads throughout space. The discovery took an effort from a group of 3,000 scientists that dedicated endless hours to the cause that would surely bring our species one step closer to understanding our universe. We've also discovered that all the atoms and light in the universe only make up less than 5% of the total content of the cosmos. The remaining 95% is composed of dark matter and dark energy, which are invisible, but whose effects dominate the evolution of our universe. Dark matter provides the gravitational pull that keeps galaxies together, while dark energy is responsible for the ever-accelerating expansion of our universe. For thousands of years, we've looked to the heavens and wondered what mysteries are hiding beyond the clouds. Since 1970, there have been more than 90 telescopes placed in orbit by NASA and the ESA to bring the universe closer to us. And with the James Webb telescope that launched on December 25, 2021, we entered a new era of discovery. This telescope is the largest and most powerful one ever built, and its daunting task is to find the first galaxies that formed in the early universe, and peer through dusty clouds to see stars forming planetary systems. We may not have found the theory that unites quantum with gravity yet, but every discovery brings us one step closer to that ultimate goal of unification. Throughout our time on this planet, we've pushed the boundaries of existence by asking tough questions and working tirelessly to find the answers. Our species has been defined by its incessant thirst for knowledge and unwavering hope in a unified universe. 350 years have elapsed since our first big successful step in this journey, when Newton unified the heavens with the Earth, revealing that planets, stars, and apples are guided by the same set of laws. 200 years later, James Clerk Maxwell coupled electricity with magnetism, and then Einstein linked space and time and warped them into one fabric that we now know as spacetime. Looking at the timeline of these events, it shouldn't be surprising that the road ahead could be much longer. Einstein died dreaming of a physical world governed by one set of laws, a unified framework that can unlock the mysteries of our universe, and Hawking never ceased to look up at the stars and wonder what mysteries lie ahead waiting to be found. Whether the theory of everything is a realistic quest or a delusional attempt to make sense of the absurdity of the universe, one thing is certain. Our unwavering hope in the search for unification will only lead to humanity's advancement as a species. If you feel you're in a black hole, don't give up. There's a way out.
The impact of NASA is undeniable. They have the ability to burn the importance and results of pure physics, math, engineering, and science in general into the minds of everyone they reach. Go into any middle school science classroom and you'll see posters of rockets, planets, black holes, many of which have the NASA insignia stamped right on them. If you were to ask any of those science-minded kids, what do they want to be when they grow up? They're not going to tell you they want to work for the Department of Agriculture. They're not going to tell you they want to be a defense contractor. They're going to tell you that they want to work for NASA, and that's pretty important. Unfortunately, when NASA is brought up into the public eye, as much cool stuff that they accomplish and achieve, people still tend to think it's a waste. And to be honest, I can kind of understand that point of view. Why spend money on sending chunks of metal to other planets when my job isn't paying me enough? Why should I spend my tax dollars on something that doesn't affect my day-to-day life? And sadly, this is where many people are mistaken. For starters, your tax dollars are hardly going to NASA. For every dollar you're taxed, you're not giving NASA a quarter, you're not giving them a dime. In fact, about half a penny is going to NASA. For an average American, that's about $10 a year. To compare, when you buy something off the dollar menu at McDonald's, you're paying more in sales tax than you're giving to NASA. They're pretty much running on empty all the time. And alright, I know, NASA isn't broke. $20 billion is a lot of money. Except when you realize that the US military spends this in about 2 weeks. Now this isn't a video to stomp all over the budget of the military. In fact, a lot of the technology that is developed through that funding is the reason why you have a lot of the things you do today. But when you look back, you realize that, on average, about $300 billion a year has been given to the US military since the mid-1900s. You can only wonder what would happen if a similar budget was given to NASA and other space-centric companies. In case you ever want to be sad, just take a look at this. NASA's budget going down. For a long time. From over 4.5% of the annual federal budget, down to less than a measly 0.5%. What if this wasn't the case? What if instead spending went up, through the roof and to the stars? Let's think about it. If they miraculously ended up with tons and tons of money, where would it go? Is money even the issue? NASA has been working on a little something called the Space Launch System, or SLS, for the better part of the last decade. Think of it as the BFR of NASA. This system is similar to the Saturn V, the rocket responsible for all the feats NASA accomplished during the space race. It's capable of launching humans into deep space missions, to the moon, to Mars, and perhaps even further. But, as is NASA tradition, it keeps getting delayed. It was first planned to fly in 2017, but that's been pushed back to 2020, and even now that deadline isn't looking too promising. With proper funding though, this project could be completed within the next 24 months at the latest. We would literally have rockets capable of putting us back on the moon on standby, waiting to be launched at any time. And funding this project is beneficial in multiple ways. Not only will it provide us the ability to carry out thousands of experiments that are just waiting to be tested on and around the lunar surface, but it supplies tons of jobs for us here on Earth. And this wouldn't be the first time that NASA has actually brought money into the economy. For example, the $25 billion spent on NASA's research and development from 1959 to 1969, which included some of the main technology that allowed us to reach the moon, continued to return money into the economy until 1987, almost 30 years later. They returned over $181 billion. Coincidentally, this $181 billion is just enough money to build an entire International Space Station and still have about a year's worth of money left over. The International Space Station is still the most expensive thing ever built. To date, it's cost over $160 billion to create. It serves as an overseeing oracle for us. It can monitor natural disasters before we can detect them here on Earth. It's helped provide medicine for some of the worst diseases known to man. We've learned more about the human body in space than anything else. Each year, NASA spends about $3 to $4 billion just maintaining and keeping the station moving forward, or about 20% of its annual budget. And this cost is only going to go up. Right now, there's 6 people in space. 6 out of 7.7 billion. Given proper funding, the ISS could expand. It could make room for new astronauts and new experiments, and perhaps even change the entire purpose of the space station in general. Instead of being a permanent and final settlement for all modern astronauts, in the future, it could serve as a pit stop on the way to other destinations in our solar system. One day, these 6 people could turn into 10. That 10 could turn into 100, and before you know it, we have an entire community of people orbiting around us every 90 minutes. When you look at that big rock that's spinning around our planet, somewhere on it lies the remains of 6 different Apollo missions from over 50 years ago. There's tons of US surveyor drones, there's multiple lunar rover vehicles that the astronauts drove around the landing sites, there's bags full of, waste? Yeah, let's call it waste. In 1973, the total cost of the Apollo program, the one that sent 12 astronauts to the surface of the moon and returned them to Earth, was reported to Congress as about $25.4 billion. In today's money, that's about $146 billion. That's about 3% of the total United States current budget. With just 3% of the national budget for 1 year, we not only accomplished the amazing feat of putting people on another world, but we quite literally built NASA from the ground up. You see, we didn't have the Kennedy and Houston and other space centers. We didn't have the equipment. We didn't have the rockets or vehicles or means of accomplishing anything. But yet, we were able to create all of it, and on a really impressive timescale. And that was just with the technology we had in the 1970s. If it wasn't for the Apollo program, chances are that companies like Intel, AMD, and Nvidia might not even be around today. These 3 companies have a massive impact on almost every device you use today, even the one you're watching this video on right now. We've been to the moon, and it could be time to go back. As we said, in the past, it cost about $150 billion for the entire Apollo program. But today, that number could be drastically lower. It could even be covered in 6 months of NASA's current budget. NASA has made claims that we could return to the moon within the next 5 years for only $10 billion. To be honest, a lot of the technology we have today is actually capable of sustaining a small colony on the moon. But the only problem is, of course, money. At first, we most likely wouldn't be living on the surface. It's too risky and we don't have the resources to stay there for long periods of time. The most likely course of action is something called the Lunar Gateway. If you've seen Interstellar or pretty much any space movie, it's about to become a reality. The Lunar Gateway will essentially act as an international space station, but for the moon. It'll be our main base of operations for everything taking place on the lunar surface. It'll serve as a laboratory for any and all work. It'll serve as a living quarters for all the scientists on board. It'll be able to hold new kinds of rovers, robots, and other technology to be put to use down on the surface. The gateway could be regularly serviced, just like the ISS. Things will start off slow, but before you know it, we could have a rapidly growing city of sorts on the moon. But what good would come out of living there? Well, it could potentially be one of the most profitable adventures humanity has ever gone on. There's a lot of metals and materials on the moon that are actually pretty rare here on Earth. There's a chance that there could be some concentrated groups of materials that are just not as abundant on Earth, like uranium, thorium, and more. And let's not forget the poles. Exploring the lunar poles of the moon is one of the most important things on the to-do list. Why? Water. To keep it short, both humans and rockets have one thing in common. We both require oxygen. If there's a substantial amount of water near the moon's poles, we could process that into fuel for ships, or air we can breathe. This would drastically reduce the amount we would have to bring all the way from Earth. Once we have the foundation, we could pretty much use the entire moon as a mining base for anything we need. Numbers estimate that, with about $40 billion, we could realistically begin planning on building a long-term, sustainable base on the moon, with only about 4 days of the United States annual budget. There's a lot of challenges to space travel, of course. How do we get rid of our trash? How do we recycle our oxygen and other resources effectively? The list goes on. Missions to the moon are about 1,000 times farther from Earth than missions to the International Space Station. So, this means that we need capable and ample systems that can reliably operate far away from our current home, support humans effectively, and still be able to be launched without being too heavy to get off the ground. It's complicated. But if we can't get to the moon with this technology, how are we expected to complete the 54 million kilometer journey to Mars? You see, the moon and Mars are linked in a way. By exploring the moon and providing ways to live there long term, we almost explore Mars at the same time. The moon is kind of like the kiddie pool of space exploration, albeit a pretty big one. Before we venture out to Mars, the moon actually gives us a chance to test similar technology that we would use on Mars. We've yet to actually stay long term in deep space environments. The ISS only orbits at about 400 kilometers above Earth, and while yes, that technically is in space, it doesn't even compare to the 380,000 kilometer distance between us and the moon, and isn't even in the same ballpark as the 50 million kilometer journey between the Earth and Mars. Living on the gateway for months at a time will give us a deeper insight as to how our bodies react to the potentially harsh deep space environment, and perhaps give us ways to prevent the worst from happening. A lot of the things we learned from space exploration are still being circulated in society today. NASA has something called the Technology Transfer Program. To keep it simple, it identifies technology that can be used outside of its intended use in space. For example, computer mice? That was NASA. The cameras in your phones? About 1 in 3 phones use technology that were originally planned for use in space. Every year, about 1,700 new products and technologies are tested and then potentially provided to you to do whatever you want with them. They're literally giving you the ability to start businesses using their technology, and for all you know, you could eventually spin one of them off into a huge company. You see, it's recursive. NASA gives out technology to businesses to use, and the money that these businesses make are then taxed. This tax money is then returned to NASA, and the entire process repeats. The more funding NASA receives, the more technology excels and gets better, and this then improves our lives even more. Since its inception over 60 years ago, in 1958, the United States has spent around $600 billion on NASA. Or, as we mentioned before, about 1 year's worth of the United States military budget. NASA has a weird business model, if you want to call it that. NASA doesn't spend their money hoping to get a return on their investment. The return is simply a byproduct of human ingenuity and genuine curiosity about the universe around us. They put their money into places where they see fit, where they see value, and all the rewards that we reap are because of our desire to learn more about why we even exist. The USA spends the most money on space exploration out of every country in the world. This is great, but in the grand scheme of things, as we saw, it's pretty much chump change. You see, we created NASA and we gave birth to all these new ideas and technologies and foreseeable barriers that we could work towards overcoming. But then we stopped. Funding went down, people stopped caring, and we've been coasting ever since. The space shuttle was an influential part of the past 30 years of spaceflight, but as we all know, it's no longer in commission. The International Space Station has single-handedly changed every single one of our lives, and yet, funding for it could be phased out within the next decade. And that piece of art that orbits our planet every 90 minutes is doomed to lay dormant, orbiting the planet with no inhabitants ever again. Because the Soviet Union in 1957 launched a 2-foot wide ball of metal into orbit around the planet, NASA was founded, and 12 years later we landed on the moon. Raw competition inspires us more than anything else. It pushes us to be better than everyone else, And that's why we were able to accomplish all the crazy things we did. When the United States realized that the Soviets were capable of landing on the moon, what happened? Well, we stopped going. We stopped caring. We'd won the space race. It's only human nature to be territorial. It's what has kept us alive for so long. It's what has allowed us to rise to the top. But the problem is, the thing that has kept us alive and made us so successful is the same thing that's keeping us from progressing even further today. It served as a fuel to create the societies that we live in today, but it also serves as a ceiling, and we're rapidly approaching it. We are literally damaging the world, the only one we know so far, to a point to where we cannot recover from it. Some of the most influential people in the world are realizing this as well. And this is why you see companies like SpaceX, Blue Origin, and many others not competing with NASA, but rather working alongside them. We can no longer wait to be helped. We have to take things into our own hands. Half a penny. 0.5%. That thin slice is responsible for all the hopes and dreams of our future. It's responsible for some of the biggest technological advances in the past 10,000 years. And yet, people still think it isn't worth it. I don't know about you, but I think this is just the start.
It's common to hear that space is the final frontier, to go where no man has gone before. But in actuality, it's the beginning of the future. The knowledge we gain about the universe increases day by day, but our means of accessing it is a slow and sometimes even painful journey. Since the 1970s, the American spaceflight industry has been moving in the wrong direction. From being able to send humans to the moon atop a Saturn V rocket, to then only being able to send astronauts to the ISS aboard the space shuttle, to now having nothing at all. Space has been a place only explored by the biggest governments on the planet. But now, the tides are shifting. If the most powerful countries on Earth aren't willing to put effort where it's due, others have to step up. The engineering feats from the 20th century have put us in a position to accomplish all of our goals, but yet, the entire reason we began has been forgotten. The reasons these rockets were built, the places we've went, the things we've achieved, it's all just been swept under the rug. Until now. The private spaceflight industry is growing at an unprecedented rate. The biggest problems with space travel are being tackled by some of the smartest and richest people on this planet. And it's not a coincidence. Space travel is one of, if not the most important issues today. It's not a cultural issue, it's not a political issue. It's a matter of evolution. We've always been explorers, moving from sea to land, to moving across entire continents, traversing oceans, covering every single inch of our planet. And now, it's time to go even further. As of 2019, only 4 entities have put a space capsule in orbit and successfully returned it back to Earth. The United States, Russia, China, and SpaceX. That's it. Elon Musk took a sum of $100 million and, in 2002, Space Exploration Technologies, or better known as SpaceX, was born. They're in a league of their own, launching some of the most powerful spacecraft since the Apollo era. SpaceX is competing with some of the most powerful forces in the entire world. Their goal is simple: to enable humans to live on other planets. And as of right now, the destination is looking like Mars. SpaceX has revolutionized the commercial spaceflight industry, and are the ones reigniting the public's interest in space travel. But the company hasn't always had the reputation it does now. The Falcon 1 rocket was SpaceX's first, and almost last venture in commercial spaceflight, but it's perhaps the most important one of them all. From 2006 to 2009, Falcon 1 attempted 5 flights, but it wasn't off to the best start.
When you had that third failure in a row, did you think, I need to pack this in?
Never.
Why not?
I don't ever give up. I mean, I'd have to be dead or completely incapacitated.
But on September 28, 2008, things went a little differently. Falcon 1 carried a 165 kilogram simulated payload into orbit, successfully. For the first time, a privately built liquid-fueled booster reached orbit. The Falcon 1 rocket is the first in the family of Falcon rockets developed solely by SpaceX. It stands 21 meters high and was capable of carrying over 500 kilograms of payload to low Earth orbit. For its time, this was the most important event in spaceflight history. 500 kilograms isn't much, but this was the start of everything. It created the roadmap necessary towards a future of cheaper and more reliable space travel. That day, that first successful flight, was what single-handedly saved SpaceX from extinction. After the first 3 failed attempts, SpaceX was on life support. The $100 million that was put into SpaceX was all gone. If this 4th flight hadn't succeeded, SpaceX most likely would have gone under, and all the things you're seeing them do today would have never happened.
I messed up the first 3 launches. The first 3 launches failed. Unfortunately, the 4th launch, which was that was the last money that we had for Falcon 1, the 4th launch worked, or that would have been it for SpaceX.
Simply putting something in orbit is one of the hardest tasks there is, and all these failures show how challenging the process really is. But they had done it, and it saved everything. On December 23rd, 2008, NASA awarded commercial contracts out to private spaceflight companies, 19 of which went to a company called Orbital Sciences, while 12 went to SpaceX. The contract was valued at over $1.6 billion. From this, SpaceX was saved, and they boomed. In a good way this time. In 2010, SpaceX developed Dragon, and, yet again, made the world's first commercially built spacecraft to be launched and recovered successfully from orbit. The Dragon spacecraft is the future of manned space travel. It can deliver not only cargo, but is also capable of carrying up to 7 passengers to Earth orbit and even beyond. Also, in 2010, a new addition to the Falcon family would be introduced. The Falcon 9 was made with reusability in mind. It's a 2-stage rocket with 9 Merlin engines, that's over 3 times the size of the Falcon 1. Both of these, the Falcon 9 rocket and the Dragon capsule, were launched together for the first time in December 2010. A year and a half later, they were sending Dragon to the International Space Station, becoming, yet again, the first private spacecraft to dock at the ISS. Since then, they've been doing routine resupply missions to the ISS funded by NASA. So far, they've done over 18 resupply missions with only 1 failure, and they have no plans of stopping. With all the success of the Dragon spacecraft, let's not forget about the Falcon 9 itself. After years of work, in 2014, the first test flight of the Falcon 9 reusable took place. The rocket is the same as any other Falcon 9, but now, the rocket was capable of lifting off of the ground, launching into the sky over 250 meters, and, after hovering, returned back to the launch pad, in one piece. After more testing, they decided to try and test these for real. But, just as the Falcon 1, it didn't get that great of a start. But, you can only mess something up so many times before it starts to go your way.
5, 4, 3, 2, 1, 0. Liftoff of Falcon 9.
For the first time, we had reusable rockets, and spaceflight was changed forever. SpaceX, on a 2-stage Falcon 9 rocket, had successfully launched 11 satellites into orbit around the Earth, and returned their first stage back to Launch Pad 40 at Cape Canaveral, Florida. Just 4 months later, in April 2016, they made history yet again. Falcon 9 launched Dragon on a cargo resupply mission to the ISS for NASA, and for the first time, landed the first stage of the Falcon 9 back on Earth.
on a drone ship in the middle of the Atlantic Ocean. SpaceX had proved that they could not only land a rocket back on land, but also with extreme precision on a barge in the middle of the ocean that's less than 100 square kilometers in size. These launches are quite literally changing the world, each and every time. But let's get bigger. The Falcon Heavy is an engineering masterpiece. Tens of thousands of hours of work, years of innovation, all with one goal in mind: carrying humans into space, returning them to the moon, and even beyond. The liftoff thrust of the Falcon Heavy is the same as 18 Boeing 747 aircrafts going at full power, all at once. To even try and compare the two is embarrassing. The first stage of the rocket is composed of 3 different Falcon 9 cores, with a total of 27 Merlin engines all firing simultaneously. It's essentially like you're launching 3 different rockets at once and making sure that they all work together. Shortly after liftoff, the center core slows down to conserve fuel, while the 2 side cores use almost all their fuel, saving only a portion of it. Once the fuel is exhausted, about halfway through the flight, the side boosters separate and return back to the launch pad for a simultaneous landing. As for the center core, it's used to push the payload into orbit. It'll be going too fast to return back to Cape Canaveral, so once it's completed its mission, it too will return to Earth, but not on land. It'll land on a barge approximately 1,300 kilometers off the coast of Florida. 1 rocket, 1 launch, 3 different landings. The space shuttle that NASA used from 1972 to 2011 cost approximately $60,000 for each kilogram of material to be sent into orbit. The Falcon Heavy can do the same thing, but for just 1,300. Nothing else even comes close actually. With the ability to lift over 64,000 kilograms, a mass greater than a 737 jet with passengers, luggage, crew, and fuel, the Falcon Heavy can lift over double what the next closest competitor can do, at a third of the cost. If there's any rocket that's currently being manufactured in the modern age that is capable of sending humans into deep space, it's the Falcon Heavy. It's the most powerful rocket in the world currently in use, and the fact that you can save and reuse over half of it makes it the most efficient rocket ever made. Reusable rockets are a necessity. Why? In order to live on other planets, the only way that will be feasible for the masses is to reduce the cost of spaceflight, drastically. Right now, the Falcon Heavy costs about $90 million per launch. If we can engineer these rockets to have a lifespan of 100 launches, and we're looking at under $1 million per launch. Compare this to the Saturn V in 1969, which in today's money cost a few $billion per launch, and you'll start to see the power of reusability. Just the first stage of the rocket accounts for over 75% of the total cost. The fuel used on a Falcon 9 launch is cheap when compared to the price tag of the rocket, coming in at only around $250,000 per launch, or about 0.3% of the total cost. A Boeing 737 costs around $100 million on average. Compared to the Falcon Heavy at around $90 million, it's essentially the same. Now imagine that every time we take a flight around the world on one of these planes, we destroyed it afterwards. Imagine that every time we drove to work or school, we had to destroy the car. But yet, when it comes to spaceflight, rockets tend to fly once and only once, despite the rocket itself being the majority of the cost. This doesn't make much sense. Looking back on history, reusability is the common denominator when it comes to widespread access to anything. If cars couldn't be refilled and taken on multiple trips, nobody would own them. If airplanes were all simply one-way flights and couldn't be reused, no one would be flying. Imagine having a rocket with humans that could be launched, sent to orbit, returned to the surface, refueled, and then launched again, multiple times, in the same day. This is the key to affordable space travel. All we have to do is perfect it. Once perfected, an even bigger rocket in development by SpaceX will revolutionize the way we travel. The BFR, or Big Falcon rocket, will be over 118 meters high. It's over 2.5 times as strong as the Falcon Heavy. It's a spacecraft with 7 engines on top of a booster, named Super Heavy, with 31 more Raptor engines. It's capable of carrying over 100,000 kilograms of material not only into low Earth orbit, but to Mars as well. If a base is set up on Mars, it could refuel, and then go even further than that. With the BFR comes Starship. It's just the top part of the BFR. Instead of putting payloads in orbit or sending us on deep space missions, it can also be used for travel on Earth. Starship is a system that will bring some of the shortest travel times humanly possible. You will be able to reach anywhere on Earth in under 1 hour.
Imagine the commercial uses for this. You could work anywhere in the world and have a commute shorter than you would today. You could order a package and have it sent to you from across the world in hours. Visiting friends and family would be easy, and the term long distance starts to lose its meaning. The designs of the BFR change year after year. When working on revolutionary ideas, chances are you're not going to get it right on the first try. Historically, SpaceX is the biggest example of that. But when you realize that the Starship itself is more powerful than the Falcon Heavy, the advancements in rocket technology will start to become apparent. With spaceflight, reusability is the only way we could ever even think about leaving Earth and venturing anywhere else. Without it, costs will remain too high, and the dreams of going anywhere else but here will remain just that, a dream. But SpaceX are the ones leading the charge. They're the ones who are tackling the problems that nobody else will. While governments across the world push their space agencies to the sides, private companies will rise up. These are the ones who are building the future of our species. These are the ones who are reigniting the interest of space travel in everyone's minds. And these are the ones who will fill in the gaps and go even further beyond what anyone else in the world is doing. If you're uncertain about the future of SpaceX, I think we should just look back at Elon's previous ventures. SpaceX's missions and their reusable rockets will impact space travel the way PayPal affected monetary transactions, the way Tesla impacted electric vehicles, and the way Neuralink will impact our biology. 15 years ago, everyone was skeptical about SpaceX being able to even launch a rocket. But they did. People were skeptical that they'd ever be able to land a rocket. But yet, they did. Even recently, people doubted that the Falcon Heavy would work. But, of course, it did. 10 years ago, they had just gotten their first rocket into orbit. Fast forward to today, and they're making their mission statement a reality. So looking at the plans of SpaceX, there's a good chance that you're looking directly into the future as well. In 2015, SpaceX, for the first time, landed the first stage of the Falcon 9 back on Launch Pad 40. But directly adjacent to that is Launch Pad 39A. It's also owned by SpaceX, except the story behind it is what gives me faith. On my birthday, July 20th, in 1969, men first stepped foot onto the moon and changed the world, our species, forever. Just 4 days earlier, at 9:32 a.m., they loaded aboard a Saturn V rocket and launched into space. They had left Earth on a mission that no one else had ever done before them. But once the smoke and dust from the launch pad had settled, there lied Launch Pad 39A. The same launch pad that SpaceX is using today to launch the biggest and most powerful rockets ever made. The mystery of human existence lies not just in staying alive, but in finding something to live for.
Okay, all flight controllers, go for landing. Retro, go. Fido, go. Guidance, go. Control, go. Telcom, go. GNC, go.
July 20th of 2019 marked the 50th anniversary of mankind's most treacherous journey, when Apollo 11 astronauts Neil Armstrong and Buzz Aldrin first touched the lunar surface. Over 500 million people around the world, 20% of the Earth's population at the time, sat eagerly in front of their televisions as they watched the crew descend from the lunar module and take the most famous steps in history.
That's one small step for man.
The story of Apollo 11 is one of the most important events in the entire history of humanity. It's one that will be remembered for thousands of years to come. But this grainy television footage only tells part of the story. The technological complexity of the mission, alongside a risk that very few people on the planet were willing to take. Very few actually understand how difficult this mission really was, and how many things could have, and almost did, go wrong. Apollo 11. Its 3 crew members: Commander Neil Armstrong, Lunar Module Pilot Buzz Aldrin, and Command Module Pilot Michael Collins. On July 16, 1969, they launched from Kennedy Space Center at 9:32 a.m. EST atop a Saturn V rocket, the most powerful machine ever built by humans. When John F. Kennedy made his proclamation to go to the moon before the decade was out in 1962, this left NASA only 7 years to conceptualize and create a rocket that could push humans to the moon. The end result was the Saturn V rocket. The behemoth stood at over 364 feet tall and weighed upwards of 6.5 million pounds when fully fueled. It included multiple stages,
just as modern rockets do. But from this 111-meter machine, this is the only thing that would return to the Earth. It's one thing to build a skyscraper. It's a whole different task trying to lift it off the ground. Which is why it took over nearly 8 million pounds of thrust in order to get the Saturn V into the sky. As of 2019, it remains the tallest, heaviest, and most powerful rocket ever used by mankind.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.
The first stage burn from the rocket lasts around 3 minutes to get the rocket clear from the launch pad and into the sky. It then detaches and falls to the ocean from about 30 miles up. The second stage burn then begins and continues for another 6 minutes to push the astronauts into space. After that, the S-4B third and final stage of the rocket burn begins and gets Apollo 11 into their correct orbit around the Earth. 1.5 Earth orbits later, around 2 hours and 45 minutes after liftoff, the third stage of the Saturn V reignites for a second burn that lasts around 5 minutes, forcing Apollo 11 out of the Earth's gravity in an event called the translunar injection. The crew is now hurtling towards the moon at nearly 7 miles per second. But their job isn't done just yet. The transposition and docking maneuver begins. The Apollo 11 spacecraft consisted of 3 main modules. The Command and Service Module Columbia, where the astronauts would spend most of their journey, served as the main quarters for the astronauts. It was a place they could work and live, except it was only the size of an average car. There's a single button inside the command module that, once pressed, will essentially blast away the panels that were once used to protect the lunar module. Once this happens, the command module uses small thrust rockets to separate the spacecrafts. The command module pilot, Michael Collins, would then rotate 180 degrees and dock with the lunar module. The new joint spacecraft then separates from the third stage of the rocket. They're now in the configuration needed to enter lunar orbit. From sitting on the launch pad at Cape Canaveral, to reconfiguring their docking situation in space, to now being on course to the moon, the launch of Apollo 11 is concluded just 3.5 hours after liftoff. And now, we wait. During their journey, Apollo 11 broadcast live footage from inside the cabin back to Earth for the entire world to see, in perhaps the most iconic television broadcasts of all time.
The entire continent, North America, down to the Yucatan Peninsula, Cuba, and then I run out a window.
In this small command module, with nothing but inches of aluminum protecting the crew from the emptiness of space, they showed the world what was possible, and what was to come. But for now, for the next 3 days, they'll be silently drifting away. "75 hours into the mission, on July 19th, with Earth over 206,000 miles away, Apollo 11 reaches the moon. After flying behind the far side of the moon, contact with Earth was lost. But also came the first lunar orbit insertion burn. For this to take place, the spacecraft would have to make yet another rotation. Now flying engine first around the moon, a 357-second engine burn would place the spacecraft into their initial orbit.
God, that's a big beauty. Gigantic crater. Look at the mountains going around it. My gosh, they're monsters. Oh, there's a big fella over here, too. Look, another picture of that big fella. Yeah, that's a big one there. Look at those craters in a row. See them right going right out there?
Now successfully orbiting the moon, the real intentions of the mission begin. Current space missions usually involve extreme precision, and Apollo 11 was no different. Except in one way. Rather than landing at a precise location on the moon, their objective was to just land safely in a rough area, and hopefully live to tell the tale. The odds of landing, in the astronauts' own words, were about 50-50.
Good view there, Neil? Yeah, sure do. Well, it's beautiful out there, isn't it? Man, this is really something.
Every previous Apollo mission led up to this moment. Apollo 8 was the first actual mission to the moon. However, they didn't land on the surface, but were rather put into an elliptical orbit around the moon. Apollo 10 was essentially the same, but they went a bit further. Astronauts Thomas Stafford and Eugene Cernan entered the lunar module and reached an orbit of just over 8 miles above the surface of the moon, the closest approach that any humans had ever made until that point. They could practically touch it. These missions drew a line all the way from the surface of the Earth all the way to 50,000 feet above the lunar surface. All Armstrong and Aldrin had to do was land from there, and finish what the previous missions had laid out for them. At around 100 hours and 12 minutes into the mission, the descent to the surface began. Armstrong and Aldrin loaded into the lunar module Eagle and separated from the command module.
Roger, Eagle, contact.
Roger, how does it look?
The Eagle has rig.
Roger. You got a fine looking flying machine there, Eagle, despite the fact you're upside down.
One more orbit around the moon, about an hour and a half later, and the descent engines fire, placing the lunar module into a lower orbit, a trajectory nearly identical to Apollo 10's. The lunar module had 3 different landing programs that would be cycled throughout the landing process. They are, in order, P-63, P-64, and P-66. Each of these had different purposes and had to be carefully executed.
Mission 10%.
First, P-63 is run. This is the braking phase of the landing. It ignited the engine with the sole purpose of shedding horizontal velocity so it could essentially begin falling out of orbit. P-63 lasts around the first 8.5 minutes of the landing burn. The first 3 minutes of that are flown with the lunar module windows facing down. Why? This allowed Armstrong to view landmarks on the surface and make a note of what time they were passing them. This turned out to be crucial.
Right on. My position check downrange shows to be a little off.
Roger, copy.
He noted that they were passing landmarks on the surface around 3 seconds early. This seems very small and almost insignificant, but it meant that they would land nearly 3 miles away from the intended landing spot, and almost into an area unplanned for. After these first 3 minutes and the position checks had taken place, the lunar module was then rolled 180 degrees, so the windows were now facing away from the surface. This rotation allowed the landing radar on the module to actually see the surface of the moon, allowing them to now have constant updates on their velocity and altitude relative to the surface. Around 5 minutes and 15 seconds into PDI, a massive problem exposed itself.
Program alarm. It's 1202. 1202. Okay, engine stop. APA at a descent. Mode control both auto. Descent engine command override off. Engine arm off. Port 13 is in. Houston, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
Thank you.
You're looking good here.
Okay, we're going to be busy for a minute.
102 hours, 45 minutes, and 39 seconds after liftoff, the lunar module touched down in the Sea of Tranquility. They used almost every last bit of fuel trying to find a landing spot that was suitable. It's like driving a car with the gas gauge on empty. You could run out at any second. No one knows exactly how much, but estimates say there were 15 seconds of fuel left. The flight plan called for the first steps on the surface to begin after a 4-hour rest period, but considering they had just landed on the moon for the first time ever, sleep wasn't exactly their first priority. The EVA was moved ahead, and they began suiting up. 109 hours and 7 minutes into their mission, Neil Armstrong began descending down the lunar module.
Okay, Houston, I'm on the porch.
Roger, Neil.
I'm at the foot of the ladder. The LEM footbeds are only depressed in the surface about 1 or 2 inches, although the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Yeah, I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Buzz Aldrin follows him outside, nearly 20 minutes later.
Jake, ready for me to come out? Okay, now I want to back up and partially close the hatch. Making sure not to lock it on my way out. Particularly good thought.
For the next 2 hours, the moon's population, for the first time in its existence, changed from 0 to 2. They spent their time collecting samples of rocks and dirt, taking photographs of everything in sight, which included both astronauts. Scientific experiments were also left on the surface. A seismometer, which would be used to measure moonquakes, was left right outside the landing area. A retroreflector was also left, and is used to measure the exact distance between the Earth and the Moon. The TV camera left on the surface allowed everyone to see things firsthand. In that moment, despite all the conflict on Earth, despite social status, despite wealth or intelligence, every person was one. We had made our mark on another world, and this signified that. But before you knew it, both men returned to the lunar module. At 111 hours, 37 minutes, and 30 seconds into the mission, the last footstep on the moon was taken.
Anything more before I head on up, Bruce? I think it is. Head on up the ladder, Buzz. Adios, amigo.
And now, sleep. After spending less than 24 hours on the surface, 2 men changed the world forever. They were now set to be reunited with the command module and sent on their way home. But this was yet another even more dangerous task. The Saturn V on liftoff had 5 engines on launch, but Eagle had 1. It is the one and only way to get back into orbit. It's the only way home. This also couldn't be tested on Earth in the same conditions that it would be in on the Moon. The first and only firing of the ascent engine came during the real thing. The lunar module only had enough oxygen for 2 men for 2 days. If something had broken during landing, or if the engine didn't ignite for any reason, there was 0 chance for recovery.
And you're cleared for takeoff. Roger, understand. We're number 1 on the runway. 9, 8, 7, 6, 5. Port stage, engine arm ascent. Proceed.
Luckily, fate was on our side. "128 hours in, Columbia and Eagle are reunited successfully. It's time to head home. Everything went according to plan. All that's left is to make it back alive. The trans-Earth injection maneuver begins. A 2-minute and 30-second burn will place the rejoined Apollo 11 spacecraft into a trajectory to bring the crew back to Earth.
Roger, this trip of ours to the moon may have looked to you simple or easy. I'd like to assure you that has not been the case. Our large rocket engine on the aft end of our service module must have performed flawlessly, or we would have been stranded in lunar orbit. The parachutes up above my head must work perfectly tomorrow, or we will plummet into the ocean. Only through the blood, sweat, and tears of a number of people, the American workmen who put these pieces of machinery together at the factory. All you see is the 3 of us, but beneath the surface are thousands and thousands of others. This has been far more than 3 men on a voyage to the moon. More still than the efforts of a government and industry team. More even than the efforts of one nation. We feel that this stands as a symbol of the insatiable curiosity of all mankind to explore the unknown. To to all those Americans who built those spacecraft, who did the construction, design, the test, and put their heart and all their abilities into those crafts. To those people, tonight we give a special thank you.
On the 9th day, 195 hours in, it's time for re-entry. Moving at over 36,000 feet per second, the spacecraft is literally compressing the atmosphere so tightly that the bottom of the command module is experiencing temperatures as hot as the surface of the sun. And inside are 3 astronauts hoping to make it back safe. And then nothing. Due to the sheer heat of re-entry, ionized air forms around the spacecraft, causing all radio communications to be lost. For the next few minutes, this blackout will be one of the most stress-inducing moments of the entire mission. You can't track them, you can't speak to them. All you can do is wait. But if you wait long enough, things might not turn out so bad. Apollo 11 is, simply, the mission of carrying men to the moon, landing them there, and bringing them safely back. They did just that. The Apollo astronauts are, without a doubt, some of the most courageous humans to have ever existed. To think about these men, all of which who had families, kids, lives that they left behind, to go on quite literally the loneliest mission in the past 1,000,000 years. They left behind everything they knew, including the only planet they've ever known. The only place in the known universe that's habitable. Command Module pilot Michael Collins was perhaps the loneliest man in existence during this mission. Every lunar orbit, as he passed behind the dark side of the moon, all communications were lost, with the ground and with the men on the surface. For those 47 minutes, he had himself, and only himself, to keep him company. No human has ever experienced this level of solitude in the history of mankind. But once they made it home, they weren't so lonely anymore. They were superstars. From complete and utter solitude to global recognition almost overnight. This image, although it seems just like another moon photograph, is different. This photo contains every single person alive in existence at the time, except for one. Michael Collins orbiting the moon. That's everyone, right there. A snapshot of humanity from our nearest neighbor. And although it has been over 50 years since that historic day, it's not the end of our journey. We came in peace for all mankind, and without a doubt, we will return.
It's nighttime. Work is over, dinner has been eaten, and you're just about to go to bed. You lay down for a short while, but your mind decides it's not done with the day just yet. You think you let ideas run their course, but you are still not tired. You decide to pull the curtains to welcome the night sky into your room. It's bright outside. The sky is radiant, you noticed, but only barely, as your eyelids slowly start collapsing under their own weight. You start drifting away, and just as you are about to close your eyes for the night, you glance upward. It's the moon. Our moon, a celestial constant in an otherwise ever-changing sky. Under its glow, you fall asleep, reassured that no matter what, the moon will be there all night, just as it has been for millennia. Our moon has pledged its allegiance to Earth for a long time now, almost for as long as the Earth has existed by some estimates. But this loyalty has not always been rewarded with the attention that it merits. The moon and its understated presence, both in the night sky and in our ambitions of becoming a spacefaring civilization, have been gathering the limelight as of late. Not one, but 2 major developments regarding the moon in the short span of a month. On October 26, 2020, NASA's SOFIA
short for Stratospheric Observatory for Infrared Astronomy, discovered the presence of water on the sunlit surfaces of the moon. Now, while the presence of water on the moon is not surprising news, any significant amount detected thus far had only been in the darker, shadowed parts of the moon. By the way, the moon has no dark side. All the sides are lit, but it just so happens that the moon is tidally locked to the Earth, which means that we see the same side of the moon every night. It has, however, poles. It is in these poles that water was previously discovered. These poles were able to store some water because they were protected from the otherwise extreme temperatures on the rest of the moon's surface. The lack of an atmosphere means that temperatures on any given lunar day can fluctuate by more than 200 degrees Celsius. That meant that whatever water that could have been on the moon would quite easily just evaporate off. This is why the presence of water on the sunlit surfaces comes as such a surprise. It's where you would least expect to find it. The amount of water is still minuscule, even when compared to the water content of some of the harshest deserts on Earth. Yet, the mere fact that there seems to be a mechanism that is generating, or at least storing water, is of great significance in humanity's next chapter in space exploration. On the other hand, China's Chang'e 5 spacecraft launched moonward on November 23, 2020. Its mission is to try and understand the history of the moon by bringing back lunar rocks that are younger than any of the samples we already have. The samples that are supposed to be brought back are 1 billion years younger than the ones collected by Apollo. Scientists intend to study the late-stage volcanism that should answer questions about the moon's younger surfaces. It's a short 23-day mission, after the end of which we should have a clearer picture of how our rocky neighbor came to be. This mission is one of a series of missions that, in theory, should culminate into the International Lunar Research Station in 2030. But, given how close the moon is, it's actually quite surprising how we still do not know so much about it. For one, we're still not totally sure how it was formed. We have theories, of course, the likeliest of which is a spectacular one. According to it, the moon was the result of a collision between the Earth and a Mars-sized planet named Theia. The impact from the collision ejected material that eventually morphed into what we see today as the moon. This theory seems most likely because the composition of lunar rocks brought back from the Apollo missions is very similar to what can be found on Earth as well, suggesting they were from the same source. There are theories still about whether that initial collision led to the birth of just one moon or two. This is because the crust on the moon is not even. Parts of it are significantly thicker than others, and scientists believe that it could have been caused by a collision on one side that led to the uneven thickness. Regardless, the moon was far from the gentle orb of light we see today. Soon after it formed, it was a fiery ball of magma, but even at its hottest, most ravaging state, our cosmic companion was already preparing Earth to harbor life. You see, like how the Earth tugs on the moon too tugs on the Earth. The gravitational pull goes both ways, and as such, soon after the collision, the moon's pull is what helped to stabilize the Earth's axial tilt, allowing the seasons to exist. Had it not been this way, we would have had a barrage of ice ages and extreme warm climates all at the same time. This axial tilt and its consistency are down to the size and number of the planet's moons. In fact, the Earth is the only planet among the 8 major ones to have one moon. Mars, on the other hand, has 2, but both are rather small, and as such, Mars wobbles about 10 degrees from its normal tilt of 25 degrees. We also have the moon to thank for stirring up the primordial soup with its power to influence tides. Without that, organisms may have never amassed enough nutrients to form into complex life forms. In the early days, the Earth was spinning 4 times faster than it does now, but over time, that has slowed down to the 24-hour days we have now. But why is there an uptick in talks about the moon lately? Well, for starters, there's the Artemis program, which is an incredibly ambitious program that intends on having the next man and the first woman on the moon in the next 5 years. While we have already been to the moon, this time, scientists seek to learn how these astronauts could spend prolonged periods in space to be better suited for longer space travel, such as the subsequent colonization of Mars. You see, in the scale of outer space, the moon is really, really close, and given we have already visited it numerous times already, it's quite surprising that we haven't visited it again in such a long time. Recent discoveries, though, stir up some much-needed excitement about the moon. While it has been overlooked in the past few decades, having a colony on the moon is the next logical step in our space endeavors. Water is obviously one of, if not the biggest concern in having a stable presence on the lunar surface. Now, this is important for both drinking and jet fuel. Jet fuel contains the very same ingredients as water, hydrogen and oxygen. The recent discoveries certainly shed some optimistic light on the possibility of using this water. But scientists could also use the solar wind and the hydrogen that came with it and combine it with the oxygen found in lunar dust. This would give us even more fuel to bunny hop around even further into the solar system. Speaking of solar wind, we also need to think about protecting ourselves from the harmful radiation in space. Solar wind is essentially charged particles from the sun that are constantly being ejected into space. They move extremely quickly and are upwards of 1 million degrees Celsius. Particles don't sound dangerous, but the radiation most definitely is. It's no wonder then that astronauts who have been to the moon have shorter lifespans than their earthly brethren. Besides, one of the reasons you see so many craters on the moon's surface and not so many on ours is that the moon simply is not big enough to hold onto an atmosphere so that asteroids would burn up on entry. It's also why there's no insulation on its surface, which is why you see the crazy 200-degree temperature differences between day and night. All these things pose a significant risk for a future colony on the moon. You and I take our atmosphere for granted every day, but had it not been there, even something as small as an intergalactic grain of sand would have the velocity many times that of a bullet and could cause a lot of damage. All of this has led scientists to consider lava caves as a possible place to live. When the moon was still an active fireball, lava seeped through some of the layers of its surface. It eventually cooled down, as we know, and lava dissipated. But the pathways it took remained. Those lava caves offer protection from both the speeding debris and the temperature extremes. The absence of an atmosphere and thermal insulation is obviously down to the moon's small size, but while the size is a disadvantage for these aspects, it is a tremendous advantage in others. The small size of the moon means that the gravitational pull on its surface is much less than compared to that of the Earth. 1/6, in fact. That would mean that the same rocket will require significantly less energy to lift off from the moon than it would to need to lift off from the Earth. That is why a colony on the moon is the next logical step. Another reason why the efforts to colonize the moon could set up the scene for larger efforts later is its geopolitical implications. Conquering the moon famously became the focal point of the tensions between the United States and the USSR. But beyond showcasing humanity's ability and what it can achieve when it's truly motivated, the Cold War also showed that adversaries can and do come together out of a mutual concern for their own safety and rights. Both the US and the USSR agreed to a treaty in 1967 that would allow free access and prevent natural appropriation of celestial bodies, including the moon. This law holds to this day. Today, the adversaries have changed, yet the competition remains. While this competition should spur technological innovation, we have to wonder what its implications will be socially and politically. If there is indeed a colony, who gets to go? Who gets to live? On a planet sort of void of other resources, light is power. Very few sections of the moon get regular sunlight. Who gets authority over those sections? These are social problems, not technological ones. And as such, the moon here is not so much a blank slate, but a template for interplanetary policy. Not just for Mars and any other planet we colonize in the future, but also for the pale blue dot we are already on right now. The moon actually moves away from the Earth about 4 centimeters a year. We know this because the Apollo astronauts actually left a retroreflector on the surface that scientists can point lasers to. So, it seems our companion in the night sky is leaving us, slowly but surely. Or is it? You see, once the spin of the Earth and the rotation of the moon are equal, neither party will be tugging at each other any more than they need to remain in orbit. It is at that point that the moon will stop moving away from us. However, when all these forces cancel each other out, the solar wind remains unaccounted for. Far into the future, that force will cause enough drag to slow the moon's rotation, so much so that it starts coming back closer to Earth. And given enough time, it will come so close that the Earth's gravity, the endearing force that held it so close for all this time, will actually rip the moon apart. The moon will return to where it came from, but that isn't destined to happen for another 50 billion years or so, and it's way more likely that the Earth will be swallowed by the expanding sun before then. And when the lights go out for one last time, the moon will actually accompany us, just as it has always done this whole time. The moon really will be there with us forever. From the birth of life to our inevitable demise, the moon will witness all of it.
Earth and civilization as we know it has come a long way in the past 200,000 years, and has experienced a